So welcome. Today we're going to talk about AC currents, and we did a little bit of this on lab, and I think we did the first part of this in class last time, but we'll go over it again. And what we'll see is that it's kind of neat actually. So basically, first thing, we are making AC, alternating currents, by having a coil that moves inside a magnet. That's pretty much how your power station works, and that's how, little generators work. That's how you make alternating current. You have a coil that moves inside a magnet, and basically the faster you move, the more you spin the coil, the higher the frequency, and different countries use different frequency electricity. In fact, the United States and Britain, as you might expect, use different frequencies. I think in the United States it's 50 hertz, and in Britain, in America, it's 60 hertz. So, and that raises some issues like in Japan, which during the reconstruction phase after the Second World War, there was British companies came in and American companies came in, and so in the country they have different systems in different parts of the country, and 50 hertz doesn't talk to 60 hertz very well. So so we're spinning in the United States, we spin this at 60 cycles, 60 hertz, and we get a nice sinusoidal curve. I call it sinusoidal simply because I'm starting off at that point. If I had chosen to pretend like I start off like that, I suppose I would call it a cosine curve. But it's the same shape no matter what I choose. And what we did before was we recognized that that is one period, and I can represent that as a circle. If I put a circle to the side, I start off on the axis, I then go positive, I then go back to the axis, then go negative as I go around there. So both of those represent the same thing. This is called a phasor, and it's really useful. And we're going to scratch the surface of its utility, but electrical engineers really get into phasors. So, and so I can represent my AC signal as a linear wave progression or as a phasor. And I'm trying to show you the correspondence here, which would be nice if I didn't have a mistake in it. So this point A is actually before you get to the 90 degrees. There's the 90 degrees, and you've not in time got to the 90 degrees yet. So you've not in time got to the 90 degrees there. So there's my A, and this guy is wrong. And then there's my B at that time. And then here's my C at that time. And then down here is my D at that time, etc. So I can represent this thing as a phasor. Why is a phasor useful? Because there are times when my voltage graph, although it's got the same shape as my current graph, they are displaced from each other for various reasons. And so sometimes it's the angle between the voltage and the current through a component that is important. So okay, and of course this omega is in radians per second. If I want to deal with it in hertz, then I need to convert. So omega equals 2 pi f, which comes from 2 pi over t. 2 pi because there are 2 pi radians in one circle. As I think we said last time, the first problem we come into is the fact that because it's a symmetrical relationship between the positive and the negative, what does this mean? This means the current flows one way for half a cycle, it flows back again, and one way and back again. So the current, the electrons in a piece of wire with AC don't go anywhere. They just go backwards and forwards and backwards and forwards in that piece of wire. Whereas with DC, eventually an electron that left the battery will actually go through your lamp. With AC, that need never happen because they just go backwards and forwards and backwards and forwards. Okay. We have an equal amount of positive flowing current as we have negative flowing current, so the average is zero current. Well, that's not really the effect. If I have a big current going through me, I will get burned. And it is no comfort that on the second part of the cycle, it will go through me the other way, you know. So, and the other thing is a little current will have the same average as a big current. It basically, averaging repetitive cycles like this is a really futile thing to do because the average comes out to 0 no matter what it is. We want somehow to give an indication of, if you like, the power. And so we've got to somehow deal with this problem of averaging to 0. And so what we learned to do is we learned that in the olden times, the analog way of solving this was basically you squared your current. Well, -2 times -2 is +4. So all the negatives become positive. Now, all my signal is on the positive side. It's still got these missing bits, so I can time average this, and I will get a lower value than the peak values. And then I remember, remember I squared this, so I need to get rid of that square. So you square root what you did, and you get down to a more reasonable value. So let me draw that in blue so that it looks more like purple, say. So there's my answer. And what did I do? I basically squared, and then I meaned, and then I rooted. And for some reason, I've never been able to work out why, we call this the root mean square, not the square mean root. We do it in the reverse order. We name it in the reverse order. We squared this thing, then we averaged it, meaned it, and then we square rooted it to get the scale back. We call it the RMS. And basically, the RMS current equals the maximum current, the original maximum current, over the square root of 2 because of the shape of this thing. And this equals 71%, so 0.71 times Imax. And frankly, I tend to just remember 71%. If I will look at a voltage trace, then I will get my VRMS is equal to Vmax over root 2, which is 71% of Vmax. And if I'm using Ohm's law, delta V equals IR, in an AC circuit, I can ask you, what is the current corresponding to this voltage going through this resistor? Yeah? Just like we did for DC. But really, I should say, what is the peak current caused by this peak voltage going through this resistor? Or I should say, what is the RMS current caused by this RMS voltage going across this resistor? So I can use Ohm's law. If I'm working with peak, I've got to stay with peak, and if I'm working with RMS, I've got to stay with RMS, and it works. There's no problem. Where it doesn't work is when I get to power. Power is equal to delta V times I. Yeah? You know, what was it? Joules. Voltage is I'm drawing a blank now. Voltage is joules per coulomb, and current is coulombs per second. So when you multiply them together, you get joules per second, which is power, which is watts, which is what I want. So power is great, but I cannot use the peak voltage and the peak current, because if I picture it, there's my peak voltage, and here's my peak current. And in the life of this piece of wire, they're only at the peak for an instant. It's a very unrepresentative number to put in. And so most of the time, you got much less voltage causing much less current to flow through that piece of wire. So you're not going to emit as much heat. Yeah? So we need to somehow get a representative average voltage and a representative average current, and that is what RMS is used for. So with power, you must use RMS. You cannot use peak. So there's the catch. Ohm's law, you can stick with peak and peak, and you stick with RMS and RMS. It's up to you. But power, you cannot. It's meaningless to put in. It's incorrect to use the peak voltage and the peak current. Okay. And so, I don't know if we did these last time, but an AC current has an amplitude of 10 amps. What's the RMS value? So here's my amplitude. That's Imax. And that equals 10 amps. So I RMS is equal to I max over root 2, which equals 0.71 I max, which equals 7.1 amps. And then 15 volts, so here's my picture of it. So now this is V max, and it equals 15 volts. So V RMS is equal to V max over root 2, which is 0.71 times V max, which equals 15 times 0.71, which is 10 point. It's going to be 7.1 plus 3.55 is 10.65. 10.65 volts. You know, it's somewhere in there, and that guy is somewhere in there, you know. Okay? Now comes the meat of what we're going to do today, which is we are going to try to analyze a circuit that looks like that. We've got an inductor, a resistor, and a capacitor. And the first thing I've got to tell you is if you look this thing up in your textbook, it will probably call it a RLC network. And I have no idea why historically we call it that. It's not very helpful. It turns out that, as we'll find out from the analysis, for a series combination of these resistors, of these components, there's the inductor leads and the capacitor lags behind. So I prefer to call these LRC, because why not just learn it that way, and then you know the order, you know. Maybe I'm missing something that some electrical engineer will say, well, later on, that's not such a good idea, but, you know. As far as I'm concerned, it helps me to remember LRC, because then I know the order that I'm going to need them in the end. We have what can you tell me? You know, electricity consists of voltages, currents, powers, whatever. What is constant through the L, through the R, and through the C? Thinking back about your simple circuits, what can you tell me should be the same through your L, through your R, and through your C? Would they have the same voltage across them? Would they have the same current through them? The current is the same because it's a series network. So that's going to be our link. The current will be the same. Now, sometimes the current is big, sometimes the current is small because it's an AC signal. But the current's going to be the same, yeah? The wacky thing is, and we've seen this a bit before when we had the capacitor and the resistor. Sometimes the capacitor had all the voltage, and sometimes the resistor had all the voltage and all that kind of stuff, yeah? So we're used to the sum of those two potential differences equals the EMF, yeah? Remember that from before? What's going to be really strange this time is that the voltages have a vectorial relationship to each other. So the voltage dropped across the resistor is on a phasor diagram at 90 degrees from the voltage dropped across the inductor or the voltage dropped across the capacitor. That's incredibly strange. It means I can't arithmetically add those voltages together, and that's very unusual. We haven't had that before. When we did our resistor capacitor, we just added the two values together. We didn't do it, but if we did our inductor capacitor, we'd have added those two values together. That's because we were dealing with constant voltages, constant currents. Well, with the slowly changing currents. I mean, the current did change, but not, well, dug a hole for myself. It changes, but I want to say slowly. It's certainly not doing a sine relationship. But here we're going to get, and I'm going to explain to you why, we're going to get a vector relationship between these voltages. And so that makes this thing, we've got to develop some way of dealing with that. You can see down here in this graph here that although I'm showing the different relationships between the voltage across the current and the voltage across the resistor and the voltage across the inductor and the voltage across the capacitor, although I'm showing them, it's not clear exactly how they're going together. It's kind of complicated pattern, so I need a simpler way of thinking about this. And that's where phasors come in. Now, who cares about this circuit? Well, we care about the circuit because what you find is if I look at, I'm going to call it resistance, because it's in ohms. If I look at the resistance across my capacitor in terms of frequency, how, not 60 hertz, but maybe 100, maybe 500, maybe 1,000 hertz. If I look at that, what I find is that for my capacitor, for my inductor, it goes, the resistance steadily gets higher as the frequency gets higher. So this device here is very resistive at high frequencies. So at high frequencies, it's carrying most of the potential difference, and it's closing us down. Very little current. If you like, at high frequencies, this is choking us off. Not much current's going to flow through my signal, through my device. And at low frequencies, I find so this is my inductor. Low frequencies, I find my capacitor. And from the capacitor at low frequencies, my capacitor kind of kills me. So at low frequencies, this thing's choking me off. Most of the potential difference is across my capacitor, and not much current is flowing through my system. But there's this sweet spot in the middle. If I add these together, now in my mind, I'm going to add them arithmetically, just let me do that. It turns out it's not so bad, but I just talked about adding things vectorially. If I add these things, I see that there's a sweet spot here, which is a minimum resistance, which means a maximum current. And that occurs at some frequency, which I call my resonant frequency.
So is that what we did yesterday?
Yeah, that's exactly what you did yesterday. So, okay. So there's a frequency for any LC combination, which is my resonant frequency. And if I try to drive the circuit at a higher frequency, I don't get much current flow because of the inductor. And if I try and drive it at a lower frequency, I don't get much current flow because of my capacitor. But if I drive it at my resonant frequency, I get the maximum current flow. And so the analogy is you have an antenna that leads to an LRC network which feeds a speaker. And I have one radio station that's coming in at high frequency. It's picked up, but its frequency is so high for the way my circuit is tuned, I don't hear it because there's not much current associated with that radio station because the frequency is too high. And if I have a radio station that's too low a frequency, then at that frequency, although it's received, although the signal is received, the inductor is choking off that signal, and so there's not much current flow associated with it, and so I don't hear that radio station. But if I have the radio station that my radio's tuned for, then I'm at this sweet spot where I get a maximum amount of current flow, and that's the one I hear. I can amplify that signal, and that's the one I hear. So when I turn the knob on an old-fashioned radio set, now you press buttons. Well, now you probably go here. But in the old-fashioned ones, you turned a big knob, and that big knob was attached to a big capacitor, which was variable, and you were literally changing this capacitor. So you were changing that value, and so you were stepping along the frequency to go from one radio station to the next. And the radio stations couldn't be too close together, because if they were, you'd be kind of close to that sweet spot. And so you'd hear a little bit of a second station, because the stations are not pure, you know, their frequency is like that. It's not perfect. So maybe that edge would be where your sweet spot is, and you'd hear a little bit of it if they were too close together. And so the government had to make so, you know, you can only be at, you know, 89.7, and you have got to be at, you know, 91.5. And you can't be at 89.8, because we'll hear them both. So one better than the other, but we'll hear them both. And that was the situation. Radio stations had to be separated. The better the circuit, the more it's able to discriminate. So if you had really good circuits where you could discriminate really well, you could put radio stations closer together and everything. So that's what the technology has been driving for over the last 80 years, is getting that. One of the big breakthroughs was frequency modulated signal processing rather than amplitude modulated signal processing, which tended to separate things a bit better. But even so, there's so much bandwidth, and there's only so many radio stations you can have, and they're worth money. So if you bring in new technology, which means you're more resolved, you make money. I mean, it's literally twice as many radio slots. You know, I'm going to sell them to twice as many people. So a lot of money on this. There's a lot of things to do on this. That's the game we're going to play today. So I'm going to go back, and we're going to start basically here. And we'll look at each of these components in turn. So here's my resistor, here's my power supply. You show a power supply for AC with a little curvy thing inside. And my voltage at any given time is equal to the maximum voltage times the sine of my frequency times time. We did this with oscillations and waves. Remember back in the day? We did this before. Okay. So let's do a bit of electronics with this. We know from Kirchhoff's rules that the EMF plus the potential difference across my resistor must add to 0. That's the loop rule. And I know the potential difference across the resistor is going to be equal to delta V max sine omega t, because that's my EMF thing. So okay. So current in AC tends to be shown as little I. It's not an imaginary number. It's just little I, okay? So DC, AC. It doesn't matter. If you put down that for AC, it doesn't matter. But if you see little I in a book, I don't want you to kind of, oh man, so complex numbers suddenly came in, you know. Because later on, complex numbers do come into some of this stuff, but not now. So little I. So the little I through my resistor is equal to, well, this is Ohm's law, delta V max over R, modified by this sine omega t term. Well, delta V max over R is I max. Well, this is a bit straightforward. My current at a given time is simply equal to I max times the sine of omega t, just like my voltage at a given time was equal to V max times the sine of my omega t. And if I were to get an oscilloscope and plot these things out, what I'd see is when Vmax was 0, Imax was 0, and Vmax was a maximum, Imax is a maximum. When Vmax is 0, Imax is 0, and Vmax is a minimum, Imax is the minimum, or maximum negative, we can say. Minimum gets a bit, what's maximum negative? So they're in phase with each other. You get the peaks when you get the peaks, and you get zeros when you get zeros. And for many people, this is a more self-evident way of plotting that, because I pick a particular point in time. Doesn't matter where, but I pick a point in time. And I say, well, at that point in time, I've gone that far around my cycle. So I've gone that far around my cycle. And both of them have gone to the same extent. So we have both lines are pointing in the same direction. One's bigger than the other, because one's a bigger number than the other, but they're in phase with each other. So with currents flowing through resistors, they're in phase. That's an important point to remember. And if I want my maximum current, then I recognize that, well, my maximum current occurs when sine omega t equals 1. So my maximum current, that sine omega t equals 1. So my maximum current is V max over R max. Okay? So that's the pattern we're playing. Now I'm going to try and do the same thing with the inductor. Now I want you to notice a couple of things. I'm going to have an expression for my voltage in time. I'm going to somehow try to write this out. I'm going to try to write these out and then look at the relationship. This is a sine omega t, that's a sine omega t. And I'm going to end up trying to derive an expression down here. Do that same thing. If you like, I know we didn't derive it this way, but if you like, we can develop the idea of what R is through this thing. More math, but look at the big picture. So now we have an inductor with a power supply, and I know that the voltage created on my power supply plus the voltage drop across my inductor equals 0. And I can write an expression for the voltage created, a voltage drop across my inductor. It equals to L di by dt. Okay, so I know the voltage in time, it's V max sine omega t. And so substituting in, rearrange as well, I have L di by dt from there. L di by dt is equal to this V delta V, which is V max sine omega t. And so then I can take that little bit of time to the other side, and I get Li is equal to delta V max sine omega t, that's what I had just before, over L, bring the L down, times dt. Integrating, well, if I integrate all my little bits of I get the total I, so I through my inductor is equal to delta V max over L integral, because they're all constants, sine omega t dt, which gives me this equals minus delta V max over omega L cosine omega t. So now let's think. the voltage was a sine omega t, but the current is a cosine omega t, out of the math. Cosine omega t equals minus sine omega t minus pi by 2. That's basically saying there's a 90-degree phase difference between them. So I can substitute this back in and saying, well, if you want things in terms of sines, I can write this expression down here as simply saying it's delta V max over omega L sine omega t minus pi by 2. So when I look at these two, I see that the difference in terms of the frequency, or the, if you like, the phase angle, is that there's a 90-degree difference between them, and that my current lags. You see that? You don't have to be able to repeat any of that. They're great if you follow it, but I'm not going to ask you to repeat that. But what you would see if you had an oscilloscope was, you'd see your voltage would be in front of your current by, well, if you think about it, that maximum occurs at that minimum, and that maximum occurs at that minimum, that maximum occurs at that zero, and that maximum occurs at that zero, and there's a 90-degree quarter wave between the two. Yep. Quarter wave between the two. And 90 degrees, pi over 2 phase difference. 90 degrees, pi over 2 phase difference. Can I hand wave my way through this? I know that my back EMF depends upon di by dt. Yeah? That's the slope of this. So when that's got a zero slope, that should have a zero value. When that has a maximum positive slope, that should have a positive maximum value. When that has a maximum negative slope, that should have a maximum negative value, and so on. So I can get this relationship by just inferring it from the slopes, but mathematically there it is. I can represent this better, I think most people would agree. It's more clear on the phasor diagram. Now, the book references things to the voltage because that's where we start off from. But in the end, we know the current's constant. So I'd like to reference things to the current. And what I see is that my voltage across an inductor leads the current. And so I want to say LR, and I'm going to put C down, because the voltage in the inductor leads, the voltage across the resistor is, and as we're going to see in a minute, the voltage across the capacitor lags. So for me, although the book represents it, the book just follows the math, and they go, oh, okay. Then eventually they go, oh, by the way, you know. And to my mind, I know where I'm going. So to my mind, the key point is reference to the current, and the voltage leads in a capacitor, in an inductor. The voltage leads. So I say LRC, not anything else. Next little thing is, well, we said I max equals delta V max over omega L. So let's have a look. We're here. That, when it's maximum, is equal to that. Because the sign goes to 1 for a maximum value. So I max is equal to delta V max over omega L. And man, you know, that reminds me of I max is equal to delta V max over R. It just looks like it, you know. Oh, this omega L is mathematically taking on the same role as the resistance does. So let's call it inductive resistance. Problem. Inductors have resistance. They genuinely have resistance. So I can't call it inductive resistance. So let's call it reactance. We're going to give a symbol XL. You know, this is like, you know, some puppet show of space travel from the 60s, you know. We're going to call it XL. And so we have this thing called reactance. Which has units of ohms, and it behaves just like resistance. And it's tempting to call it inductive resistance, but the inductor does have its own resistance. It has an internal resistance that, you know, I don't want to get confused with. So I have this resistive term, and it's frequency dependent. That's the interesting thing. The resistivity of my inductor linearly increases with frequency. Double the frequency, double the resistivity. So if I plot a graph of ohms versus omega or F, doesn't matter, for an inductor, it looks like that. That's why it kills you at the high frequency end. Okay, so I've invented a new term called inductive reactance. It behaves like a resistance, and I have learned that my voltage through the inductor leads the current by 90 degrees on my phasor. Those are I think the important bits. What is XL? Omega L numerically, and my voltage leads my current by 90 degrees. Let's play this same game with just the capacitor now. So again I say, well, the EMF minus the voltage across the capacitor equals 0. So my EMF equals the voltage across the capacitor, and the voltage across the capacitor equals Q over C. And delta V is equal to delta V max sine omega t. That's what's coming out of my power supply. And I can say, well, combine these. So delta V max sine omega t is equal to Q over C as time passes. And I can rearrange it. So bring the C to the other side. So C delta V max sine omega t is equal to Q. And if I differentiate, of course, dq by dt is IC is equal to dq by dt, which equals omega C delta V max cos omega t. And if I look here, I see that that's a sine omega t expression. And this here is a cosine omega t expression. And if I remember that cosine omega t equals sine omega t plus phi by 2. In the last one, it was cosine omega t equals minus sine omega t minus pi by 2. There's a minus in front because we had a minus. There's a minus. We had a minus here that came out of the calculus. And so when we did our expression here for the conversion, we had to play around with it. So we could have a minus there, and that meant having a minus there. But in this expression, there's no minus sign falling out of the algebra, falling out of the calculus. So we don't need to do that funky thing. So we just have sine omega t plus pi by 2. And so when we look at this, let's express it as a sine. So I go I equals omega c delta v max sine omega t plus pi by 2. And if I draw it, I get this. And when I look, that's sine omega t, and that's sine omega t, and the difference is I have a plus pi by 2. So now, in comparison with my current, so my current leads my voltage by 90 degrees, which means that my voltage is 90 degrees behind. So L was in front, R is, and C's behind. That's where this comes from. And remembering that, well, I max is equal to that. So I get I max is equal to omega C delta V max. So I can define now, I say I'd like something. We had I is equal to delta V over R. And then I said, you know, I was equal to delta V over XL. And you say, man, I want an I is equal to delta V over XC. Now, what do I need to do to make, you know, an XC? Oh, I see. So XC is equal to 1 over omega C. If I plot a graph of my ohms versus my frequency, my XC follows that relationship. So the inductor killed you, killed you at high frequencies, and the capacitor is going to kill you at low frequencies. Okay? So the skills. I want you to be able to determine the XL and the XC for given components at a given frequency. Can you calculate XL and can you calculate XC? I'd like you to know that the inductive voltage, the potential difference across the voltage, across the inductor, leads the current by 90 degrees. I'd like you to know that the potential difference across the resistor matches the current. I'd like you to know the potential difference across the capacitor follows the current by 90 degrees. That's what I want up to now. Okay? Can you work out what your reactance is at a given frequency? And could you tell me, oh, this is in front, this is behind? So let's play with this a little bit. What is the reactance of a 5 Henry? 5 Henry inductor when 5 radians per second AC voltage is applied across it. I'm giving you the frequency there. So my AC has an omega which equals 5 radians per second. It's not the same as it's coming out of the vanes, that's for sure. So then I go, well, hold on. I know that for my inductor, oh yeah, XL is equal to omega L, which equals 5 times, sorry, 5, that's bad choice on my part, which equals 25. What are the units going to be for this? Ohms. It's a resistance type thing. It's a frequency-dependent resistance. What's the reactance of a 10 farad capacitor? And this is, 54 hertz. That's a bit sneaky, Bonaquisti. So you say, well, XC is equal to 1 over omega C. Is that right? Let's just go back and check. 1 over omega C. which equals 1 over omega 2 pi f. 2 pi f times c, which equals 1 over 2 pi times 54 times 10. Man, what a pain that is. So, reach in my pocket and I don't have my calculator. But I'm a physics guy. So in my bag,
1080 pi.
is it 1080 pi? Okay. 1 over 1000. Yeah, 1080 pi, which equals a number. Let's just work it out. What the heck, I don't care. 1080 times pi equals, and then we did our inverse. So I go inverse. Wow, that's which equals, I need to pick some different numbers for this. 2.9 times 10 to the minus 1, 2, 3, 4, 10 to the minus 4 ohms. Okay. Then the next one, can you do this one for me? That's going to be 10 ohms, and this is 25 hertz. So what is R going to be equal to? What is the resistance of a 10 ohm resistor when a 25 hertz AC voltage is applied across it? Whose birthday is it this week? Whose birthday is it this month? Whose birthday is it in the next 6 months? I know none of you are going to have birthdays by the end. Whose birthday is it in the next 9 months? So you don't have to answer. If you got that uncomfortable feeling, it's usually because you've been tricked. So what is the resistance of a 10 ohm resistor when pardon? 10 ohms. Because this is not frequency dependent. So it's just 10 ohms. So it acts like resistance, but it's frequency dependent. So see how much fun teaching is? Oh, by the way, let me just stop. 2 things. So now we get to this next stage where we say, okay, so we've got this expression for, I'm sorry, I'm going the wrong way. So now we go to this stage and we say, let's put these 3 guys together. So we have a frequency dependent resistivity with our inductor. We have a frequency dependent resistivity with our capacitor, and we have a non-frequency dependent resistivity with our resistor. And if we put an oscilloscope across these bits, so we look at the voltages across these bits in time, we find they're all over the place. When the voltage across the resistor is a maximum, there's no voltage across the inductor and there's no voltage across the capacitor. When the voltage across the capacitor is a maximum, there's a negative voltage across the inductor and there's no voltage across the resistor. And it's like, oh man, we're all over the place. And it's because of this phase angle issue. So we say, consider a series network consisting of a resistor, inductor, capacitor. The current in all parts of the series AC has the same amplitude and phase. The instantaneous voltages are out of phase. So we can say the voltage drop across the resistor and the voltage drop across the inductor and the voltage drop across the capacitor are out of phase with each other. And so we got to add them up vectorially. And this is the easiest way of adding them up. We draw it on a phasor diagram because we see, oh, the voltage drop across the capacitor is always at 90 degrees to the voltage drop across the inductor. So they're always fighting each other. And the voltage drop across the resistor is always in between those two. I'm sorry, yeah, the voltage drop across the inductor and the voltage drop across the capacitor are always 180 degrees away from each other, and the voltage drop across the resistor is always 90 degrees away from both of them. And so how do we take this into account? And the easiest way to take this into account is not actually to look at voltages, but to look at resistivities, or resistances. And what we see is we have our XL, and we have our XC, and we have our R. And so we can say we have XL minus XC, and we have our R. And so we get this resultant, and that is called Z, which is our impedance. It impedes, impedance, I think it is. It impedes the flow of current. And when our impedance is a minimum, we get the maximum current flowing through. So I need you to be able to work out XL at a given frequency. I need you to be able to work out what XC is at a given frequency. I need you to be able to draw this diagram showing XL, XC, and R. I need you to be able to work out what the Z is and what the angle is between the Z and the R. Those are the skills. The Z is Pythagoras. It's just R squared plus XL minus XC all squared. And your angle, tan to the minus 1 of XL minus XC over R. If you know the diagram, it just falls out, yeah? Yeah, so XL always goes in front, XC always goes behind. At low frequencies, we're going to get a big XC and a small XL. So at low frequencies, we'll get something that looks like that. And at high frequencies, we'll get something that looks like that. And in the middle, we get something that looks like that. Now, what do you notice about this middle one in terms of the XL and the XC? What do you notice for this middle one?
Oscillate at the same rate.
They're the same size, aren't they? And so the resultant of the top and the bottom is 0. So the impedance at resonance is just the resistance of the resistor. Yeah? When these two guys are balanced, when that guy there is balanced by that guy there, no matter what size they are, the fact is they cancel each other out. And so we end up with the impedance is just the impedance of the resistor. So skill so far. Can you calculate XL? Can you calculate XC? Can you draw the phasor diagram? Can you work out what Z is? Can work out what phi is? Can you do those things? That's the skills that I want. No power losses are associated with pure capacitors and pure inductors in an AC circuit. But power is converted into heat in the resistor. So it's the resistor which radiates thermal energy. For an LRC, let's write it down like that circuit. The instantaneous power is that. Man, okay. Remembering that and substituting gives that. So P average equals 1/2 of that. P average equals that, which equals I squared R. There's the take home. Your power is I squared R. That's the heating effect of your resistor. Gotta fly. If I want to know where the resonant frequency occurs, it comes out of this, and it is omega naught equals 1 over LC. I need you to know that. So XL, XC, Z, phi, phasor, omega naught. No, get to know those. What happens is, as the resistor gets smaller, this peak gets sharper. And that's important. That's your discrimination between one radio station and the next. So we can define this thing called the quality factor. And the quality factor is basically the full width at half the maximum. So it's omega naught divided by delta omega. I'm sorry, it's the full width compared with the actual value of the resonance. So it's omega naught over delta omega, which turns out to be omega naught L over R. So the bigger the L and the smaller the R, the bigger, the sharper the peak is. Last little thing. So don't worry so much about that. Just know it exists. Okay? Last little thing. We spoke before about mutual inductance. When you have a transformer, you can link what goes on the AC at the primary with the AC at the secondary by this expression, which is not written down there. It's V1 over V2 is equal to N1 over N2. That's the best one to remember. The ratio of the voltages is the same as the ratio of the number of turns. So if I go from 10 to 40, my voltage is 4 times bigger. If I go from 10 to 50, my voltage is 5 times bigger. So I can step up voltage or step down voltage by my choice of my number of turns. I can't get something for nothing, so I'm giving something up. In getting this bigger voltage, I get a lower current because power equals IV. Power, I1 V1 equals I2 V2. There's no way around that. So know that simple transformer relationship. And that's it. So transformers, I love transformers. Transformers are going to be on there. There's going to be a question about AC theory. It's going to be on there. And then why not give you something on RMS values? Why not? Okay? So...